Good day, students. Welcome to math.serve.com, where we don't just solve, we teach. In this clip, we're going to be going over the power rule. We're going to start off by taking a look at what the power rule is. So what is the power rule? Let's go ahead and write it down. Power rule. So if you're looking for the derivative or the instantaneous rate of change of a function expressed as x to the n, the power rule helps us to determine that the derivative of x to the n is n x to the n minus 1. This notation of writing the derivative d dx of a function is known as the Leibniz notation. Okay? This is the person that came up with this notation. Now, there's another notation for the derivative due to another mathematician called Lagrange, and that is the prime notation. So d dx of x to the n can also be expressed as x to the n prime. Okay, and if we apply the power rule stated above here, we're going to have nx to the n minus 1. d dx and prime of a function represents the derivative. They both mean exactly the same thing. Okay, and this notation prime is due to a mathematician called Lagrange. Now, what is this formula telling us? What is the process? Let's take a look at what the process is using the symbols, and then we will take a look at some examples. Okay, so this is the process. Let's say you're to find the derivative d dx of x to the n. What this formula is telling you to do is, first of all, you take a look at the power of the polynomial term. Okay, it could be a rational term too. Okay, you take a look at the power, then you power it down. That becomes n. Power down the exponent, and then you mark down the exponent by 1 by subtracting 1 from it. So you power down or mark down by 1. Okay, and then that gives you the final result for the power rule, which is n x to the n minus 1. Okay, so there's the process. Now, what does the power rule help us to accomplish? Why is it good to know the power rule? Well, why? Well, the power rule helps us to find, so let's write this down, the power rule helps us find the instantaneous rate of change, also known as the derivative. So a process can be modeled by x to the n. Now, how would you be able to calculate the rate of change of that process? The power rule can help us to find the instantaneous rate of change or the derivative at an instant of that function. Generally, we can describe them as functions that can be expressed as powers with numerical exponents. Okay? So if you can express a function as a power where the power is a number of any kind, then you can apply the power rule in finding the instantaneous rate of change or the derivative at any x value or point in time. All right, there's some neat little shortcuts from the power rule that is good to have mastered in order to really hasten your process of differentiating functions. Okay, so we're going to go ahead and take a look at those shortcuts that really facilitate the power rule process. Now, the derivative of a constant. What is the derivative of a constant? What this question is asking is, what is the rate of change of something that's unchanging? Let's say you have a horizontal function. What is the slope of that function that's constant? The rate of change is 0 because nothing is changing. It's as though you have a car that's not moving. If you look at the speedometer, what is it going to say the speed of the car is? The speed is going to be 0 because the car is maintaining a constant position. It's not moving anywhere. Okay, so that's what the derivative of a constant is. This is known as a constant rule. Now, what if you're taking the derivative of a linear function of the form ax. Now, what is the derivative of a linear function? Or in other words, what is the slope of a line? If you have a line in the form y equals mx, the slope is the derivative. The slope is constant, and the slope is m. So the derivative, or the rate of change of a linear function at any x value, is given by the coefficient of x, which is a. This is another shortcut to keep in mind. Okay, and then we have the power rule itself, d dx of x to the n. We know what this is. You power down the exponent, and then you mark it down by 1. Now, what if you have the derivative of a constant, times a power x to the n? All you do here is you factor out the constant, and then you apply the power rule to the polynomial term, to the power, okay? So power down the exponent, and then mark it down by 1. So your final form will be a n times x to the n minus 1. So these are some shortcuts that can really help you to differentiate powers rapidly. Okay, let's take a look at the first example. Examples. Number 1. So let's say if y equals 3x, and we're to find dy dx in this question. Okay, so we have y equals 3x. We're to differentiate both sides with respect to x. So we have d dx of y is equal to d dx, the derivative or the instantaneous rate of change of 3x. Okay, now on the left side, we'll simply have dy dx equals, now before we differentiate this function, can you see what the final answer is just by inspection? What we're differentiating, the function that we're differentiating, is a linear function of the form ax. Now, if we go back to the shortcut that we talked about earlier, what is the derivative of ax? The derivative is simply a, the slope of the line, right? So we have a line here of the form y equals mx. So can you see that the derivative is automatically going to be 3? That's what the answer is if you're making use of the shortcut. But what I'm going to do, I'm going to show you the long way of doing it, okay, to confirm that the derivative is in fact 3. So first thing we're going to do is we're going to use the constant multiple rule to factor out the constant from the polynomial term, and then we're going to be differentiating x. Okay, we want to express it as a power. So how do you write x as a power? It's x to the first power. Okay, x to the 1 is x. Okay, now if we apply the power rule there, what do we have? So bring down the 3, and then the power rule, you power down the exponent 1, and then you mark it down, the exponent, by 1. So that leaves us with 3 times 1, which is 3, x to the 0th power. X to the 0 is 1, so you have 3 times 1, which is 3. And that's exactly what we concluded that the answer was going to be based on the shortcut that we discussed earlier. Okay, let's take a look at question number 2. Question 2, what if we were to find y prime where y is equal to 4 plus 2 over root x plus x to the 3rd. Okay, now what we're going to attempt to do first is express each term as a power if possible or applicable. Okay, so let's go ahead and write down what we're going to do. Express each term as a power if possible or applicable. Okay, sometimes you have a power that is consistent with one of the forms of the shortcut, and you don't have to bother yourself expressing it as a power. Okay, now we have y equals 4 plus 2 over root x plus x to the third. Okay, so 4 is a constant. Okay, every constant is a power of 0th degree. Do I have to write this as a power? As possible is not applicable here because I can simply apply the shortcut to differentiating constants. So whenever you see a constant leave it alone, you don't have to express it as a power. Now this right here is a rational radical, so we can try to express this as a power, okay? Now how about I use the property of exponent to express this radical as x to the 1/2. Okay, and then x to the third is just x to the third is already a power, so it's in a nice form. Going further, we have 4 plus. Now we're going to use the reciprocal property of exponents to express x to the 1/2 as x to the negative 1/2. Okay, when the denominator goes to the numerator, you invert the sign of the exponent. That's the reciprocal property of exponents. Okay, now that we have powers or terms that we can use a shortcut for, we can go ahead and carry out our term by term differentiation. Okay, so we're going to find y prime. What is y prime? Y prime is the same thing as dy dx, it's a derivative, okay? With respect to x equals 4 prime, the derivative of a constant function plus 2x to the negative 1/2, derivative of this rational function, and plus the derivative of x to the third. Okay, so this is known as the sum and difference rules of derivatives. If you have a sum or difference of terms, the derivative of the sum or difference of terms is basically the derivative of the individual terms that you're adding and or subtracting. Okay, so you can distribute a derivative across pluses or minuses. That is what this is telling us right here. That's not the case with multiplication and division. Okay, so keep that in mind. All right, so y prime is equal to, using the constant rule, the derivative of a constant is 0 because it's not changing, so it doesn't have a rate of change. We're going to apply the power rule here and also the constant multiple rule. Factor out the 2, power down the power, x to the, mark down the power by 1. Plus, the same procedure applies here. You power down the power and mark down the power by 1. Okay? Now let's see, y prime is, if you would simplify these two numbers right here, 2 goes here 1, 2 goes here 1, we have negative x to the negative 1/2 minus 1 is simply negative 1/2 minus 2 over 2, which is negative 3 over 2. So we have x to the negative 3 over 2 plus 3x to the 3 minus 1 is 2. Okay, so there goes your final answer, but we can still express it as a rational function, the first one because of the negative exponent. So we can write this as negative 1 over x to the positive 3/2. Applying the reciprocal property of exponents, if you have a negative power, you can reciprocate the term with the negative power. All right, so it becomes positive. Add to that 3x to the second power, and that is y prime, the derivative or instantaneous rate of change of y at any x value. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this presentation beneficial to you, do give us a thumbs up. Your positive feedback is very valuable to us. Do not forget to subscribe to our channel for updates to the remainder of the differentiation review series. If you have any questions about the contents of this presentation or any calculus questions in general, just place your questions in the comment section below, and we'll be glad to address it at our earliest convenience. More clips can be found on math.serve.com. Thanks again for watching. Have a wonderful day.